Right. So I think that the time has come to introduce our speaker, who is Mohamed Aouane, first-year PhD student, began quite recently. He will tell you about the team that he's working with, but he's going to speak to us about inelastic neutron scattering of endofullerenes. And with that, I will mute myself and let Mohamed take over until the question and answer session. Okay, please begin, Mohamed.
Thank you, Henry, for the introduction, and thank you all for tuning in. I'm here to present my work as a PhD student here at the ILL in the Computing for Science group, and it revolves around the study of endofullerene via inelastic neutron scattering. So before starting, I'd like to take a minute to introduce my supervisors, whether here at ILL, who are both Stefan Olds and Mark Johnson, or at the University of Southampton, and who happens to be Malcolm Levitt. And we have plenty of collaborators, whether still at the University of Southampton with Richard Withby and George Bacano, or here at ILL with the other members of the CS group or members of the spectroscopy group. So, as an outline for this talk, I'll start by a very brief introduction about what a fullerene is, before moving on to what an endofullerene is, and not specifically their synthesis and their history with the neutrons, and finally presenting some of my results. So, what's a fullerene? Well, basically, fullerene is yet another one of those carbon allotropes, and in my case, it's a C60. So it's composed of 60 carbon atoms, and it alternates between 12 and it's composed of 12 pentagons and 20 hexagons. And it is a highly symmetrical molecule, which is shaped like a football. So that's just a building block for what a fullerene is. And moving on to what an endofullerene is, it just happens to be a fullerene which has an atom, a small molecule, trapped inside of it, which makes the C60 look like some sort of nano laboratory where your trapped atom is perfectly confined in all 3 dimensions of space, which gives you a perfect opportunity to study all of its quantum states, whether vibrational or rotational ones, or anything related to spin isomerism. And you also have the fundamental aspects of a particle in a box, which we will see and talk about later. So in order to study these endofullerenes, you have to synthesize them. And to synthesize them, chemists use a technique referred to as molecular surgery, which happens to be a 3-stages process, where first you open the fullerene cage by saturating the double carbon bonds, and then putting it under an atmosphere of the atom that you wish to trap inside the C60. And then the cage is closed up. And unfortunately, there is a problem with this surgery, is that the occupation rate by the end of it is very low. Therefore, you might try a lot of times to synthesize it. You'll end up with a very small number of samples. Therefore, you have to make them count by using high flux neutron instruments, which is where the ILL plays a big role for. Okay, so before getting into my project, I want to talk about why one would use neutrons to study these systems. Well, one example is the case of water molecules trapped inside C60, where the use of neutrons can induce neutrons can induce a change in the nuclear spin of the hydrogen atoms, which means that one can see 2 transitions, a rotational transition from a para state of the water molecule to an orthostate of the water molecule. And this transition is forbidden in optical or infrared or Raman spectroscopies, but it is allowed in, you can see it in INS spectra, and that is one of the many interests of using neutrons to study these systems. Okay, so that was a brief introduction about endofullerenes, and now I will talk about what I am supposed to do during the next 3 years. It's most notably the data analysis of INS experiments for noble gas trapped inside endofullerenes, where at first I will try a numerical approach via the DFT calculations to determine the potential energy surface. And in order to understand the physics of the system for these noble gases, I will have to develop a Hamiltonian. And once these steps are done for noble gas systems, I will move on to more complex ones, notably CH4 inside C60 and C2H2 inside C60. And once we understand what happens to the vibrational states and what happens to the C60 and the trapped atom, I will study the phase diagram of C60 and the changes induced by the introduction of these atoms. Okay, so before I present my results, there is some available Lagrange data from old experiments on helium and neon inside C60. And as you can see, these low-lying modes are just the phonon modes, and these ones are the proper C60 vibrational modes. And we can see that the introduction of helium or neon inside of C60 causes a shift to slightly higher energies for the C60 modes. And if we filter the phonons out, you can see that there is an additional feature of 2 new peaks. And my job is basically trying to understand why these peaks appear and to what should we attribute the appearance of these peaks. Okay, so now this is the first part of my results, and I've decided to start by studying an argon atom inside C60 rather than helium or neon for two reasons. The first one being the availability of experimental results, unfortunately not neutron ones, but just Raman ones for argon inside C60, and the fact that I've used the size of the argon atom as an advantage, since if we trap this argon atom inside the cage, it will be much easier to optimize and stabilize the structure, because I've had that little bit of a problem with helium because I haven't been able yet to find its stable position inside the cage. So I've started with argon, which can be much easier. So moving on to argon inside C60, the first thing one has to do before calculating any vibrational spectra or anything is to optimize the structure. And to optimize the structure, I've used different functionals for my DFT calculations, whether they're LDA-based functionals or GGA-based functionals, and with the addition of van der Waals interactions. You can see that the use of the second functional, which is a GGA functional plus a semi-empirical van der Waals interaction added to it, is one that, which is the most stable structure, which gives the most stable structure, and all of my results will be drawn out from this calculation rather than these two. So the first result that was drawn was the vibrational density of states of argon inside C60. And as you can see that there is a slight shift for both these low-lying modes and high-lying modes into higher energies, which is in agreement with the available Lagrange data for both helium and neon. And also there is this appearance of this new peak around in the range of around 10 milli-electron volts, which is also coherent with the results available for helium and neon data. And so now I want to compare it with the available experimental data of Argon and C60, which is Raman data. So as you can see that there is an experimental C60 calculation for the first low line mode and one of the high line modes, which are both Raman active, and a calculation for the length of the bonds. And as I said earlier, that I would discard the LDA functional, and as you can see that there is a problem with the bond lengths. And so this is one of the reasons to explain this very important shift that appears if you go based on your LDA calculations. So this just is another proof to just discard the LDA-based functionals, whereas those based on GGA functionals, even if there is a little bit of difference between the experimental results and the simulation ones, the differences between the two are still a pretty good agreement. And so we can still keep using the results that come from a GGA calculation to base them, to use them as a base for the rest of our work. So as a small summary of what just happened, the argon atom is located in the center of the cage after the structure is optimized, which causes some shifts in vibrational modes with no negative modes appearing in our spectrum, which just confirms that the position the argon atom takes is a stable one. And also the fact that using a GGA functional yields a much better result compared to an LDA one due to the disparity in bond lengths. And that this methodology used for the calculations for argon inside C60 can be used as a good starting point for the two other systems, notably helium inside C60 and neon inside C60. Okay, so the experimental data that we had was data that came from Raman's spectroscopy, which is not the main interest of ILL, since we are mostly interested in INS data. And so I've developed a little program which can extract the SQ omega or the SQE function from the simulation results, and it is based on a multi-phonons calculation. This first term is just an elastic. It's just the elastic peak, which is not of great interest. So I've just used this second part, which is where this series is the one representing the inelastic neutron scattering part. And all of these parameters, especially this alpha and UN, are dependent on the vibrational density of state that was calculated earlier. So this is the spectrum that I obtained for argon inside C60 by trying to simulate Lagrange properties and using my simulation results. So as we can see that using the multi-phonon approach shows that they play an important role in the spectrum only for the high energy phase, whereas for the low energy one, they don't play a big role compared to the first term of the multi-phonon development. Okay, so before we end up, if there are only 2 points that you can take away from all of this, is that the calculations for an argon inside C60 have allowed me to set up a good starting point where GGA-based calculations and add in a semi-empirical van der Waals dispersion, shows a good agreement with the available experimental Raman data, and that the inelastic neutron scattering simulation shows the appearance of a peak in the same range, which is around 10 milli-electron volts as the one seen experimentally for helium and neon. And so what I've just done should be applicable to both helium and neon. As for the future work that I've already started on, is the numerical approach to carry out a potential energy scan for helium and neon, and if we try to find the most relaxed and optimized structure for these systems, and it might be the case that we are no longer dealing with a harmonic oscillator model anymore, if for the case of helium, which is a point that is also a point of interest for me, since I've started with a large atom compared to helium and neon, which is argon is behaving like a harmonic oscillator. So it might not be the case for helium, which is much smaller than argon. And once this numerical calculation of the potential energy scan is complete, I will try to do again the same thing and develop and see the differences and the shifts of the vibrational modes and try and understand them. And once we are done with the helium and neon, we'll move to more complex systems, as I said earlier, notably CH4 and C2H2. And then we hopefully will be able to carry out some INS experiments to obtain data in order to compare the simulation results. And that's about it. So thank you for tuning in again, and fire away.
Okay, thank you, Mohamed. And please keep your screen shared with us so that we can respond to questions more efficiently. So those of you out there who have a question, remember this is being recorded, and you wish to ask it, please activate your audio and also your video if you choose, but at least your audio so that we can hear your question, and identify yourself, and then Mohamed will be happy to respond. Ask your question.
Yeah, so hello everyone. Thank you very much, Mohamed, for the presentation. It was good discovery. And just a question about more details. So what exactly are I mean, I know that it is a point like to find the Hamiltonian at the end, but which are the interactions between the trap molecule and the Fullerene? So why you have this, because you are talking about the harmonic potential, and so what happened exactly for your molecule in the center? So just more details about the physical interactions.
Well, that's the point. The fact is, we're not completely sure if it is behaving as a harmonic oscillator or if it's behaving like a particle that's in a what do we call it? in a flat potential, because there might be some sort of middle ground where we have to develop a system which is some sort of hybrid between the two. So that's why we need to do all three of them, and then see maybe if the atom is large enough, it'll behave like a harmonic oscillator that's just vibrating in 3 dimensions. Or maybe if it is small like helium, maybe it does not behave like a harmonic oscillator at all. So we still need to look into that.
Okay, thank you. And could you give a little bit more details, because like my physics courses are very far away, but when you're talking about the Lagrange geometry and the calculations you did, so this slide and the multiphonons, could you just give more details about how you calculate from the simulation, just a little bit more details?
About the specific terms, or
Yes, or how you go from the simulations to the spectrum, like just more details.
Well, basically, we just needed to determine the scattering function SQ omega or SQE. By doing it numerically, we need to determine these different terms. And this the first one was this alpha term, which is dependent on the density of states that I've shown in the first couple of slides.
Okay.
So you basically just need to know the mass of your scattering center, your atom which scatters, its density of states, and this n of E, which happens to be the Bose-Einstein number. And whereas for these UN terms, it also depends on, again, on your density of states and on your energy, if it's positive or negative. And then you use a convolution method to determine your highest order terms of UN. I don't know if I've answered your question, or is it?
Yeah, no, it's more clear. Okay.
No, okay.
Okay. So thank you.
Welcome.
Can I ask? Okay.
Yes, Peter.
Thank you again for the presentation, Mohamed. It was very good. Forgive my ignorance on this. I'm not really well brushed up, but curious. You mentioned you're doing your simulations with DFT, and you had selected a number of parameters to run. You limit this number normally, right? So is there a reason why you only did quite a low number? Am I wrong? Right? Like
I don't. You mean these?
Yeah, when you add these functionals, for example, right? Normally, there's a long list of things you can add to the simulation. Is there a reason you picked these particular functionals? Is there other ones you could have used that were better? Or is it like limiting from your computational power side, or were they just not useful?
Well, the first limitation would be the ones that were available in the software that I've been using. That would be my first limitation. And also, been the ones that the results that I've obtained with the GGA ones, they're not very different. So I did not see the interest of exploring any other ones, since the atom seems to be extremely in the center of the cage. So I just did not see the point in using anything else. So
okay, yeah, that answers the question. Thanks.
Mohamed, I was just wondering, you mentioned that the yield in producing appropriate samples after the chemical surgery is very small.
yes.
You quantify that. And the other question that's related is, how do you separate the good cages that have something in them from the bad cages that are empty for producing the final sample for the measurement?
I mean, to be completely honest, this is more of a chemistry point, which I'm not very well versed in it. So I just know that the yield in the results of molecular surgery is very low. But
okay. So in other words, it's a different laboratory which is producing the samples that you've measured at Lagrange, for example.
Yeah, it's the collaborators at Southampton, which are more into chemistry.
And I guess, what was the mass of the samples you measured at Lagrange, approximately?
Okay, I can check, but
maybe you mentioned it and I forgot.
No, I did not mention the mass of the samples. No.
Monica is also tuned in, I believe. Perhaps she might remember if.
Because these experiments were done before I arrived at the ILL. So.
Yes, as far as I remember, it's around 100 milligrams, more or less.
Okay, so that's comfortable.
Around this mass.
That seems comfortable to me. Okay.
Stefan, perhaps he can confirm.
It was ranging in between 50 milligrams up to 100 and 150 milligrams, depending a lot on what endofullerene we had. But for water, it was something like 50 to 100 or something like that.
Any other questions? Wait just a little while because sometimes it takes some time to activate. Are there any other questions before we close? Otherwise, I'd like to thank everyone again. So thank you very much, and to all of you for having participated, and see you next Tuesday.